Hello there, and in this video we're going to talk about a concept that is usually tied into hypothesis testing, and that's in regards to an analysis between type 1 and type 2 errors. So before we get into that, let's pretty much set down the scenario that we're going to consider. So let us suppose you choose some level of confidence C, and it's built around some distribution. And let us assume that we choose a two-sided alternative hypothesis. So what this means is, usually we have some picture. Sometimes it's a normal distribution, but it doesn't need to be a symmetric distribution at all. But let's assume that we have some region of confidence. And this area here, this area is going to be C. And let us assume that outside here, so this region here, this is 1 minus C, which we usually represent by alpha. It's not necessarily necessary that alpha over 2 be symmetrically distributed on both sides. It could be alpha over 3 and 2/3 alpha on the other side. We don't know. But nonetheless, this is the picture that we have. And usually we have critical values on here on the horizontal axis. So this is the left critical value, and this is the right critical value. And so these critical values correspond to some confidence interval, right? And over here, this is alpha L, and this is alpha R. So here, alpha L plus alpha R is equal to alpha in this scenario. So since we choose C, then that means we pretty much indirectly choose alpha as well. So let us also recall what alpha means. So if some null hypothesis is located between these two boundaries of our confidence interval, or the test statistic is in between our critical values, then what we usually do is we're going to fail to reject the null hypothesis. And if it falls outside of this region, then we're going to reject the null hypothesis. And this is under the assumption that the null hypothesis is true. Right? So that means we can think about C to be equal to the probability of failing to reject the null hypothesis, assuming that the null hypothesis is true. And alpha is the probability of rejecting the null hypothesis when the null hypothesis is true, which we usually sometimes refer to as the type 1 error. Right? So this is C and alpha, and here's the type 1 error. So what about the type 2? Well, the type 2 is associated when the null hypothesis is false. So let's again consider our normal picture. So here's our distribution associated to our H0 true scenario. And again, here are our confidence interval boundaries. So this is our critical value L and our right critical value. So if the null hypothesis is false, that means there exists some other distribution out here somewhere, right? So this distribution is going to correspond to H0 false. And of course, this distribution is going to be centered around whatever parameter we're estimating. Sometimes that's mu, sometimes that's sigma, sometimes that's whatever it is, right? Alright, so if we look at this region still, so remember that this area here, this area right here was C, and outside of that shaded blue region was alpha. So let us consider the area between L crit and R crit, but with respect to the purple distribution. So namely the area under the curve purple, but between L and crit. So if we denote this curve as F and this purple curve as G, then this blue region C is going to be equal to the integral from L crit to R crit under F. And this red region here is going to be equal to the integral from L to R under G. So what is this area here? Well, still, this region here is the fail to reject the null hypothesis, and to the right, this is going to be the rejection region again. Rejection region. But if we talk about the purple distribution, this is under the assumption that H0 is false. H0 false, and again H0 false. And remember, failing to reject the null hypothesis is what we refer to as the type 2 error. So the type 2 error and the probability of making that is equal to this red shaded region. So this is what we usually refer to as beta. So beta is the probability of committing a type 2 error. And that's, again, the failure to reject the null hypothesis when the null hypothesis is false. And sometimes people tend to summarize this in sort of like a Punnett square type of thing. So this is going to be the fail to reject the null hypothesis. This is the rejection of the null hypothesis. This is H0 true and H0 false. So failing to reject the null hypothesis when the null hypothesis is true, that's a good thing. That's usually what we refer to as C. And rejecting the null hypothesis when the null hypothesis is true, that's usually alpha, or 1 minus C. And failing to reject the null hypothesis when the null hypothesis is false, that's beta. That's our type 2 error. And that implies that this is 1 minus beta. Some people usually represent it as pi. And for literature purposes, which we won't discuss here, people sometimes refer to this as the beta risk, and sometimes refer to pi as the power of the test. Again, we won't really dive into it now, but pi would be the outside of this red region with respect to the purple distribution. So that means all this area here. So that's going to be pi. All right, so why do we bring this up now? Because the only way we know that the null hypothesis is false, so the only way to know that the null hypothesis is false is if we know the true value of the parameter, whether it be mu, sigma, sigma squared, pi, or so on. Here, pi is the proportion. So there's some overlap in notation if you want to consider that. All right, but even though we don't know the true value of the parameter, it doesn't mean that it does not exist. So why don't we discuss this here? All right, so let's draw our distribution. Here's our critical values, L and R. And here is our true distribution. And again, here is our beta. So this is beta. That's the probability of committing a type 2 error. So let's also shade in our type 1 error. So this yellow region, which is the area outside of L and R, but with respect to the blue distribution, this is alpha. So alpha is equal to 1 minus C, and typically C is going to be chosen. And also remember that alpha is the probability of committing a type 1 error. So we can choose alpha to be as small as desired, right? So if we can choose alpha to be as small as possible, since we can choose C, so one question one may ask is why not make C be equal to 1, which will force alpha to be equal to 0? Or why not make C large and alpha significantly small? Right? C large could be 0.99 and alpha small could be 0.01. Like, what is the issue with doing this? All right, so if we make C small, so if we make C larger, then alpha gets smaller, right? So if alpha gets smaller, then what will that sort of give us? So here's our old confidence interval. So this is L and R. So let's assume we choose a new value of L and R. So let's choose L and R here. So if we choose L and R here, then that means this region here is our new region of confidence. Oh, we don't want that. We want something larger, right? All right, so let's make this a little bit bigger. And I probably don't like those colors either, right? So let's go a little bit wider. So this is L prime and R prime. Let's draw in our distribution here. So this area here, this is going to be C, and outside here, this is our alpha, which is smaller than before. So even if that's smaller than before, our fixed distribution is still going to be the same, right? So here's our true distribution. And this area here, still, this is beta, the new value of beta. So where would the old value of beta be? So the old value of beta is still going to be this area between the old confidence interval LR. So this right here is beta old. So notice what has happened here. I've pretty much widened my confidence interval. And since the type 2 error is sort of bounded by that confidence interval, since we've widened the confidence interval, our beta value is actually increased, which isn't good. So as alpha gets small, which is good, beta gets larger. Really bad. Remember, type 2 errors are worse than making type 1 errors, right? So usually we want a balance. That is, we're willing to sacrifice a decent or a relatively small, not significantly small, alpha in order to sort of minimize the value of beta. But that's pretty much just some conceptual background on pretty much why we don't let alpha to be equal to 0, or why we don't choose a 99% confidence interval. Sometimes we like to go down to 95. Some people like to go down to 90. Because even though we're increasing our value of alpha by doing this, we're actually decreasing the probability of committing a type 2 error, which some people would say is actually a good thing. But that's some background of pretty much why we don't choose these types of levels of confidence, and can sometimes give you some insight on sort of how you should choose your level of confidence when performing a hypothesis test.